In the light of the moon, a little egg lay on a leaf. One Sunday morning, the warm sun came up, and pop, out of the egg came one tiny and one very hungry caterpillar. Except this caterpillar was not like other caterpillars, for he was a student in Bio 252. His hunger was not in apples or pears or plums or strawberries. His hunger was a hunger for knowledge in studying proteins, specifically Trehalase. While most caterpillars would look for food, he looked for scientific literature. On Monday, the caterpillar studied the biological basis of Trehalase. Trehalase is an enzyme in the class of glycoside hydrolases, or glycosidases for short. As a glycosidase, its main function is in the enzymatic cleavage of the bond between two sugars, or between a sugar and another group, by the addition of water to give the free sugar. Trehalase, also known as alpha-D-glucopyranosyl 1,1-alpha-D-glucopyranoside, is a disaccharide of glucose. Linked by an alpha-1,1 glycosidic linkage between both of the anomeric carbons, the sugar is therefore non-reducing and cannot be extended beyond the disaccharide. Glycosidases in general are present in almost all living organisms, where under specific conditions they can also catalyze glycosidic bond formation. Glycosidases employ two common mechanisms in glycosidic bond cleavage, one with either inversion or retention of anomeric stereochemistry. The caterpillar learned much about the biological basis of Trehalase, but he was still hungry. On Tuesday, the caterpillar studied the catalytic mechanism of Trehalase, as viewed from an organic chemistry standpoint. Trehalase, which is an anomer-inverting glycosidase, exhibits two interesting potential mechanistic features, with the scheme following either a basic acetal hydrolysis mechanism or an oxocarbenium intermediate mechanism. Although the exact mechanism is not known, it is general scientific consensus that single or double displacement mechanisms are less likely than a more simple acetal hydrolysis in the cleavage of the glycosidic bond, though the other mechanisms are recognized. In the reaction scheme, the most important point in the hydrolytic acetal reaction is the oxonium ion formed by an attack of an H+ ion on the oxygen of the carbon-1 oxygen bond. On the other hand, the oxocarbenium ion intermediate reaction mechanism is also generally accepted. Similar to the cleavage reaction of acetal to hemiacetal involving the formation of oxonium ion, this reaction mechanism is applicable to both inverting and retaining glycosidases. Importantly, the mechanism is mediated by two carboxylate side chains, acting as an acid and base, respectively. The caterpillar learned a lot about the catalytic mechanism of Trehalase, but he was still hungry. On Wednesday, the caterpillar studied the structure of Trehalase, specifically the key catalytic residues and the binding pocket. Based on the accepted reaction mechanisms, the important catalytic residues in the binding pocket of Trehalase are two residues with a carboxylate side chain, which act as an acid and a base in the acetal hydrolysis. In yeast-neutral Trehalase, an aspartate at position 478 functions as the catalytic acid, and a glutamate at position 674 functions as the catalytic base. The aspartate 478 is located at a hydrogen bond distance of 3.7 angstroms away from the glycosidic oxygen atom of Trehalase, and the glutamate 674 is located 7.8 angstroms away from the carbon-1 atom of the glucose moiety. These two specific residues mediate the acetal hydrolysis and function to cleave the glycosidic bond. The rest of the catalytic binding pocket of Trehalase is composed mostly of arginine, asparagine, tryptophan, tyrosine, and glutamine, all of which, when in complex, are in hydrogen bonding distance of the Trehalase molecule. The caterpillar learned much about the binding pocket of Trehalase, but he was still hungry. On Thursday, the caterpillar studied the other structural features of Trehalase. The structure of Trehalase also features a tertiary structure known as an alpha-alpha-6 barrel, which is a structural feature found in all enzymes belonging to the 6-hairpin glycosidases superfamily. The active site of Trehalase is located in a deep pocket formed by the loops of the alpha-alpha-6 barrel. Trehalase also features another interesting substructure, a large lid loop over the active site. A stretch of the protein that loops out of the globular domain and back onto the enzyme, this structure can function to both shield the active site and promote ligand binding. The Trehalase lid loop is stabilized by a salt bridge between glutamate 124 and arginine 686, and hydrogen bonds between the side chain of glutamate 120 and the main chain carbonyl groups of residues alanine 696 and phenylalanine 698. These interactions stabilize the bent conformation of the loop and coordinate its tip onto the active site. The caterpillar now understood much about the structure of Trehalase, but he was still hungry. On Friday, the caterpillar studied the physiological importance of Trehalase. In insects specifically, Trehalase activity plays a role in growth and development, energy supply for flight, regulation of chitin biosynthesis, and recovery from abiotic stress. For many insects, much of the sugar energy reserve is stored as trehalose. In this way, trehalase is of vital importance in converting the insect sugar reserve into glucose, which is then catabolized to release energy. Insect flight muscles are some of the most energy-demanding tissues and are known to sustain some of the highest metabolic rates of all animal tissues. In order to maintain this high metabolic load, flight muscles use many different energy-rich molecules for catabolism, such as glucose, glycogen, trehalose, proline, phosphoarginine, and lipids. During prolonged flight, glycolysis activity in flight muscles is vital, for which trehalose reserves are catabolized by trehalase. Furthermore, trehalase activity in various insects is believed to be partly under hormonal control. For instance, in certain diapausing insect larvae, juvenile hormone ensures complete growth during diapause by controlling trehalase activity, and enhanced trehalase activity has been found at the end of diapause, following which pupation begins. Thus, these hormones play a role in controlling stage-specific insect development, such as metamorphoses, by regulating trehalase activity. Speaking of metamorphoses, the tiny, hungry caterpillar was finally full with knowledge. Now, he wasn't hungry anymore, and he wasn't a little biology student anymore either. Feeling very tired, he built a small house, sometimes called a library, around himself and stayed inside for more than a week, also known as reading period. Then, after countless all-nighters, he pushed his way out and he was a beautiful and smart butterfly.